Hello everyone, we are a team from Tongji University. We are pleased to participate in this battle and we are honored to have this opportunity to share our method of identifying leaks in L-Town. I'd like to divide our presentation into 4 parts: background, methodology, highlights, and case study. First, I will start with the background. The water distribution network is one of the most important infrastructures. However, due to many reasons such as poor quality pipes, aging facilities, and man-made destruction, pipelines are vulnerable to be damaged, thus resulting in energy waste and potential contamination. As shown in Figure 1, leakage is common to the WDN of many countries, and as we all know, leakage accounts for most of the non-revenue water. In this research, we proposed a novel multiple leak detection and isolation framework, MLDF. It contains 3 parts: calibration, identification, and isolation. A data module is also acquired. First, a gradient iteration algorithm was used to calibrate the hydraulic model after dividing pipes into several groups by the Dijkstra algorithm. Then we used STL decomposition and k-means clustering algorithm to identify the occurrence time of leaks. After that, the approximate quantity of leakages can be obtained with the help of flow forecasting. In order to locate the leakage position accurately in the shortest time, we used a stepwise leakage localization method. The meaning of the symbols that appear afterwards is as follows. The first step is to construct the benchmark leakage dataset. After hydraulic simulations are carried out separately for cases with and without leakage, we got the node pressure for those cases. Using the pressure data, we can calculate the average reference vector of pressure difference by equation 1. The second step is to narrow the area of possible leakages. The average actual leak signature can be calculated by equation 2. The similarity between delta P and delta P star is decided by the cosine distance between them. Only the pipes with the cosine distance greater than the reliable distance are considered to have the risk of breakage and need real-time leakage simulation. In the last step, we performed hydraulic simulation for cases when the real-time leakage happens on each pipe obtained in step 2. The quantity of leakage can be estimated in the identification part. Then the hydraulic feature of pipe leakage at every time step can be computed by equation 3, while the feature of real leakage can be obtained by equation 4. By ranking the average Euclidean distance between delta S and delta S star, the most likely leaky pipe can be figured out. Compared with other leakage identification methods, MLDF has 4 improvements. First, it can effectively distinct WDN's operating conditions with the help of the STL decomposition and k-means clustering algorithm. And it is insensitive to leakage size because the influence of the leakage size is removed after the normalization in equation 1 and 3. Therefore, this method is robust. Besides, due to the stepwise leakage localization and the search area narrowing step, MLDF can accurately locate the leaky pipe in a short time. Okay, now we move to the last part, case study. L-Town is a small hypothetical town and receiving water from 2 reservoirs. A pump and a water tank has been installed in the inlet of Area C, and most of its nodes are monitored by AMRs. Since the water supply in Area C is relatively independent, we can separate it from Area A and B and identify leakages respectively. According to the AMR records and the consumer types of the nodes in Area C, we can calculate the annual change of water consumption of each type. Then, with the help of the consumer types and base demand of nodes in the EPNet model, the total water consumption of each area can be predicted. According to Figure 8, it can be estimated that there was almost no leakage in early 2018. Therefore, Pipe roughness is considered to be the main parameter that needs to be calibrated. After calibration, the predicted pressure value is better fitted to the observed value at nodes with pressure sensor. With the well-calibrated model, we can simulate the leak-free conditions throughout the year, and combined with the measured data, we can calculate changes of pressure difference during the year. Then the STL is used to decompose the time series into seasonal, trend, and residual components. Since the residual component cannot effectively reflect the incipient type of leak, we determined different leak conditions by clustering the trend part to different groups. The changes in LCI means the changes of the leak state. Take the marked time period as an example. Combined with the water volume difference diagram, the amount of the leakage can be roughly estimated to be 28 cubic meters per hour, and the time range of leakage can be identified. Hydraulic simulation was carried out for this period, and the SPC method is used to accurately get the time when the leakage occurs. By performing the similar analysis on the different leakage states throughout 2019, the start time of all the leakages can be obtained. Now we come to the isolation part. In order to compare with the existing leak report, we take the leakage that occurred at pipe 158 on October 6, 2018 as an example. First, the constructed leakage characteristics are used to narrow the range of possible leaky pipes. Then real-time simulation helps to get the most likely leaky pipes in 20 seconds. The topological distance from the pipe with the highest probability to pipe 158 is only 1, which is very small, and it proves the accuracy, efficiency, and good applicability of MLDF. The distance between the leak signature of the 20 pipes in the right figure and the real leakage features is shown in figure 16. When locating the new leakage in the next period, if the current leakage has not been repaired, this leakage should be added to the hydraulic model to construct a new, quote, leak-free model. Through the above method, the identification of multiple leaks is realized, and all detected leakages are shown in this picture. This is the reference. If you have any questions, please feel free to contact us, and here are our email address. That's all. Thank you.